from 2 to 10, and then you get a steady increase from 11 to 30, and then it tapers off after about 40 items. You still get an increase by adding more and more items beyond 40, but it really does start to plateau. And that's why people have items in their scales that are somewhere around 10 to 20 for each subscale. Now I have a technical note here on languages, and that's that reliability is about data, not measures. So the reliability of the subscale scores, the composite scores from that subscale, was 0.78. You can technically say something like that and be justified, but you shouldn't say the reliability of the subscale was 0.78. Reliability is about data, not the subscale. And you'll expect reliability estimates to fluctuate even for the same scale from sample to sample. So you need to estimate your reliability for your own data and not rely upon the test manual or something like that to say that your data are good, reliable, consistent data. Estimate it for your own data because it's really only relevant to the data, not the scale. So how about guidelines? I've estimated a couple of estimates here, 0.72 and 0.83 from memory, something like that. 0.70 is commonly cited as acceptable. You see it as this, it's like this mantra. Everyone remembers this, 0.70 is acceptable. And they often cite Nunnally for this. But Nunnally didn't actually say that 0.70 was acceptable. What he actually said is 0.70, if you take together all his writings, what Nunnally really said is that 0.70 is acceptable, minimally acceptable, for exploratory research. 0.80 would be considered minimally acceptable for basic research, and 0.90 or higher is what you should observe in the data for applied scenarios. So if you were hiring people based on data, that's an important decision, or if you're making a diagnosis of depression or something like that, something important in an applied context, you want reliability to be quite high. And that is something about standard error of measurement, which I'm not going to talk about in this presentation, but I will in a future one. And if you want to look at an interesting paper by Lance et al. In 2006, it's called The Sources of 4 Commonly Reported Cutoff Criteria. What did they really say? This is where I read about what Nunnally really wrote in relation to Cronbach's alpha and the commonly cited guidelines. So assumptions of reliability. Most people don't even think about the assumptions of reliability, and you'll see people report reliability estimates without Cronbach's alpha without looking at the assumptions. And I'm only going to mention one because the other ones are more technical. I might make another video about the technical assumptions associated with Cronbach's alpha, but the main one is that it assumes unidimensionality, and that means that all the items measure a single dimension. So there's only one dimension in the data, and that's it. That's a strict assumption, and you can test that through factor analysis or confirmatory factor analysis. Now, reliability today, it is obvious that Cronbach's alpha is still used very, very commonly, and it's important to know about it, and most people will expect you to report it. But the assumptions are rather strict. Unidimensionality, for example, is often not met, and there are other assumptions that are not met, like that the error terms between the items are uncorrelated, those kind of things. And I just mentioned this briefly, that Cronbach's alpha has arguably been superseded by a coefficient called omega, and that's not something you can estimate in most commonly used stats packages like SPSS. You can get it in R if you have the right package, and I suspect it's going to become much more popular over the years. So it's something to think about. You might come across it in papers. It's a better estimate of reliability in most cases. So thanks. I hope you learned something about Cronbach's alpha here, understand what it is, and apply it in your own research, and maybe start thinking about coefficient omega.